Thank you so much for inviting me to come and give this presentation. Before I begin, I should acknowledge our funders. So a lot of the work that I'm going to talk about was done in the NWP Flooding from Intense Rainfall programme, which is one of the UK research councils, and some of it's been carried on in the ongoing data assimilation for the Resilient City project, which is funded by the EPSRC, another of the UK research councils. I'm also really grateful to my students and collaborators whose work I'm presenting. Some of them are from the University of Reading, some from the Met Office, and I've got one of your plots in here as well, Elizabeth, so from our joint work that we did. So I'm really grateful to those people. Oh, Lord. Now it's got stuck. It's not shifting. Click. There we go. Right. Press the key 6 times and it might move. Okay, so the talk's divided into 3 sections. The first section is on data assimilation, kind of a review of kilometre scale data assimilation. So I'm going to talk about the key issues for data assimilation algorithms, the key issues for observations. And then in the second section, I'm going to kind of focus in more deeply on one particular issue, which is to do with observation uncertainty and multi-scaling. And then at the end, I'll talk a little bit about the future outlook for these kinds of systems. There we go. So why are we interested in kilometre scale numerical weather prediction? As I'm sure you all know, these types of systems have been operational in many countries for years. So just as an example, the UK Met Office operational 4-kilometre model started running operationally in 2005. Obviously, since then, it's updated and is now the 1.5-kilometre variable resolution model. But these things have been around for a while. And the reason for that is because they're particularly suited to hazard forecasting. So things like convective rainfall, windstorms, fog, snow, and so on. And a typical configuration of such a system would be an hourly cycling system with a limited area model, and it might forecast maybe for 0 to 36 hours. So in the first few hours of the forecast, there's often problems with rain out and getting the system back into balance. So often in the first few hours of the forecast, the output might be blended with an extrapolation-based nowcasting system to give you the final product. All right, so some of the benefits from forecasting on these scales come from the model, and that's due to things like the improved orography and the way that convection is modelled. But on top of that, there's a significant benefit from doing the data assimilation. And there's some really nice examples of that in the paper by Gustafsson et al. In 2018. And I think David's talk might also mention some of the benefits seen. However, lots of the key issues that we first identified back in the early days of doing data assimilation for kilometre scale models still haven't been solved. And so let's just discuss some of those. I think the main issue is that often when we're doing data assimilation, our perspective tends to kind of be coloured by what happens for global models. And there's a lot of differences between what you need to do for convection permitting data assimilation from what you actually need to do for global models. So, I mean, there's some obvious things, just like the model grid spacing is a lot smaller for the convection permitting models down at the kilometre scale compared to the tens of kilometres. The error growth timescales are much longer for global models. So you're thinking about 2 or 3 days compared with maybe something as short as 10 minutes in a rapidly growing convective system. And that means that the data assimilation algorithm needs to be able to cope with non-linearity because the linear assumption is no longer valid after a much shorter period. the quantities that we need to analyze are not quite so well defined. So if we're doing a global model, we can narrow down the control variables to maybe 4 quantities of some kind of vorticity, surface pressure, divergence, and some kind of humidity variable. But on convection permitting scales, we probably need to add on to those quantities vertical velocity, temperatures, cloud, microphysical variables, surface quantities, and so on. It's not really quite clear what a minimum set would be to do it really well. Also, when we're doing the background error modeling for global models, we rely on some diagnostic relationships, things like linear balance, but we haven't got anything equivalent for convection permitting models. So we find ourselves doing fully 3D multivariate modeling. Furthermore, the statistical properties that we or assumptions that we make for global models, like quasi-Gaussian, quasi-homogeneous and isotropic assumptions that work adequately with the right variables, don't seem to work at all with the convection permitting models. And then on top of that, there's other complications, like the fact that you're using a limited area model, so you've got to worry about what you do about the lateral boundaries, and multi-scale issues, because you're getting large-scale information coming in through the lateral boundaries, and you don't want to ruin that, because that's often quite good. You don't want to ruin that when you add the extra detail with the data assimilation on the kilometer scale. So observation-wise, so we've talked about the algorithms, so now let's have a think about the observations. Well, what do we need? We need high spatiotemporal frequency, so that means fine horizontal spacings, fine vertical resolutions, and high frequency, high repeat times. We want observations that are available all the time, and in all weather. And some of the problems that we have relate to observations that might be available all the time, but we don't know how to deal with them in all weather. If we're thinking about satellite data, particularly over land and when it's cloudy, radar observations, we tend to use them when it's actually precipitating. We don't get so much information from clear air echoes. Things like aircraft are great, particularly the MODES EHS observations, because you can get lots of nice observations as the aircraft goes up and down through the boundary layer as it lands and takes off. But landing and takeoff only happen at certain times of day, not in the middle of the night, because of all the local residents near the airports. Right, so I've got this slide from Jacqueline Sugier, who has done some studies for the UMetNet organization on an observation gap analysis for the UCOS region, which is over Europe. And this is a table of requirements taken from the WMO Oscar analysis, which is sort of a look at what the observations people might actually want to have for high resolution forecasting in terms of their accuracy, the horizontal spacing, vertical resolution, the frequency of updating the observation, and the timeliness, the data latency, how quickly you can get hold of the observation once it's been taken. And the color scales, the colors just indicate whether we already have the observations that that can do this, whether we have really good observations that can do it in blue, green ones which meet kind of a breakthrough requirement, ones that might make a difference. Yellow meets a threshold requirement, meaning we've got some adequate observations, but maybe they're not amazing. And the gray means we're really falling below the minimum requirement that we need. And you can see there's very little blue on this chart. There's an awful lot of gray and yellow. So we have some major gaps in terms of horizontal spacing and observation cycle. use the new instrument MTG Metersat 3rd generation will help narrow the gap for humidity and temperature, but less so in the boundary layer, which is where we actually want a lot of information for convection permitting forecasting. So it's really not feasible in terms of the cost to increase the network density to meet those demands from that table. So what we need to do is to understand where and which investments, which types of observing instruments will have the biggest impact for now, but also for future systems. And I've suggestively written maybe sub-kilometre scale systems, but we'll talk about at the end of the talk what future systems might look like, because that's not the only option. But we need better tools to actually evaluate the impact of observations on kilometre scales. And I'll talk a bit more about that in the next few slides. We also need to do much more work to improve the impact of existing observations that we've already got. So an example here of observation impact measures on the right is FSOI for global models. So this has become very popular now. There's a routine system that's run by JCSDA comparing the FSOI observation impacts between different centres. And this plot is for satellite radiances and tells you about the different impacts of the different instruments at each different centre, with each colour being a different centre. And that's something that's quite useful because the centres can compare between them what the impacts are, and then they can understand, well, how can we get more impact in our system out of this observation type? And so it gives you kind of a basis for comparison. However, the problem with convection permitting scales is that those kinds of measures are just not applicable, because the convection permitting systems are non-linear and the FSOIs are a pretty much linear measure, and also the statistical sampling issues because you've only got your limited area to average over. Furthermore, the limited area kilometre scale models are usually designed to be particularly good for a particular weather type or season. So if we're trying to evaluate them, we might find we have some sampling issues in terms of getting enough of those types of weather. So if we really think, oh, our system's good at dealing with extreme rainfall, well, how often does that happen for us to really evaluate our systems? Indeed, with rainfall, we have to worry about spatial verification measures, because a typical problem, that Lisa even pointed out in her talk is this idea that the rainfall might be in slightly the wrong place or slightly the wrong time, and lots of root mean square type measures penalise you. They give you a double penalty for putting things in the wrong place. Furthermore, the models are often used to feed into hazard warning systems, other kinds of impact measures, maybe wind energy, so that the measures that we use to measure the observation impact actually need to be useful for the stakeholders in the forecast, as well as maybe just kind of something that's interesting for the NWP community. We actually need to make sure that we're getting good results for the variables that matter to the users of the forecasts. And I already mentioned that it would be great to be able to do intercomparisons with other systems and be able to learn from comparisons. But of course, limited area models are all slapped down on the domain of interest. So a comparison, say, between the UK model and the German model isn't very easy when the domains don't really overlap very much. Furthermore, the models themselves are optimized for the local types of severe weather that you get. So, for example, a model that runs well in Switzerland is probably pretty good at alpine mountain severe weather, but might not be very good at modeling the sorts of behavior that you have in the Great Plains of the US, in Oklahoma or somewhere like that. And finally, because of that, there's no common scorecard of measures that one could compare between systems. All right, so that's how we can measure observation impact. Well, what are some ways we might be able to improve the observation impact? Well, for the observations of hydrometeors, an obvious answer is to try and improve our understanding and knowledge of the microphysics. We heard a little bit again in Lisa's talk about the M. Varado observation operator, which is quite a complicated observation operator, which is great, except that sometimes we find ourselves with this lovely observation operator that works really well, but is a bit too slow to run operationally to try and get your forecast out if you're running hourly cycling and so on. So often we find ourselves making compromises between the best observation operator we can come up with versus CPU time. We need to worry about the physical consistency, how long the observation information remains in the forecast. And we also need to worry about whether the scales of the increments are right. Sometimes we find that we over smooth our increments if the background error correlations are too long, or alternatively that the increments are a bit too noisy and introduce noise into the system. And that's actually related again to the observation uncertainty. But if we do a really good job with the observation uncertainty, do we run into danger of overrunning the amount of time allotted to run the forecast in terms of CPU time? So I've drawn a box around those last two because that's the topic I'm going to focus on in the next part of the talk. So we're going to think about observation uncertainty. So what is observation uncertainty? Why do we care about it? How do we estimate it? How do we implement it? And what are the forecast impacts? Right, so observation errors. So one of the things we always have to remember in data assimilation when we talk about observation errors is that we're not just talking about the instrument error. We have to worry about the whole observation equation. So that means the difference between the observation and the model equivalent observation. So that takes into account the observation operator error. And an example of that for a radar observation is we know we measure a volume when we take a radar observation, but typically because we need to simplify the observation operator, we might treat that observation as a point, for example, and perhaps neglect beam bending and all sorts of other things that we know about, but we can't afford to measure to try and keep our thing, to model, to keep our thing simple. There's an issue with scale mismatch error. So in the top right there, we have an example comparing the radar and different model resolutions. So the radar gates might be every 75 meters, say, but the model might be every kilometer, a grid point every kilometer. So the radar can resolve features that the model cannot. But that doesn't have to be just that way round. So for example, if you think about the pixel size for something like Severi, that's a few kilometers, which is actually larger than the grid length of some of these kilometer scale models. So the scale mismatch error can go in either direction. The fourth one, the bottom right, observation processing. So a classic example of observation errors arising from observation processing come from atmospheric motion vector observations, which are these winds that you derive by using image processing to follow clouds around in satellite images. But you have to assign a height to the clouds, and in order to do that, you use background forecast information, and obviously that background forecast information might be wrong. So that tends to result in some pre-processing errors in the observation equation. So the instrument errors we usually assume are uncorrelated in space or time, but the other three types of errors are typically correlated. So in order to deal with the correlations, one of the things that we tend to do is to make the assumption that errors are actually uncorrelated, and then force our observations to fit that uncorrelated assumption. And the way we do that is by super-robbing. So that's doing some kind of fancy averaging. There's different ways to do the fancy averaging, but nevertheless do a fancy average. And thinning, so that's throwing away the data. And overall in NWP, we don't actually use very much of the data that we receive. For some observation types, we only use 5% of the data when we actually do our assimilation. So an example of this below at the bottom on the left-hand side is a picture from one of the Met Office radars for Doppler radar wind observations. And those are the observations, the raw observations that have just been quality controlled. In the middle, there's the super observations where the observations have been averaged from their 75-meter gates to volumes that are 3 degrees by 3 kilometers. And then the observations are thinned to every 6 kilometers. So you can see how much data we lose from the raw observation on the left to the thin super observations on the right. So what can we do about that? Well, if we actually start to take into account the correlated errors, that can lead to an increase in the analysis accuracy. So that's just an example in an idealized model on the top right there of the difference between the system using the correlated errors in black and using the uncorrelated errors in gray. You can see the analysis error is a lot smaller. Due to this work that we did with Laura Stewart, the Met Office decided to have a go at doing including interchannel correlations for ERZ data, and that led to the paper by Pete Weston and co-authors, and that they found an increase in the NWP skill score. And on an example of that is down the bottom. It's just various different metrics, and you can see that most of them produce quite a lot of good results, positive results. If we start to think about using spatially correlated errors rather than just the interchannel errors, we might actually be able to use more of the available data because we wouldn't need to thin so much in space. And we might be able to provide some more detail on fine scales from those observations. So in this next slide, I've got some plots from a paper by Alison Fowler et al. That when we we did some idealized studies comparing to try and understand the effect that using correlated errors would have and how that would interact with the background error covariance matrix B, in order to understand the sensitivity of the analysis to the observations, and also the scales that would be represented by the increments. So this is just an example. We did a number of different examples in the paper. So we are looking here at SAW matrices. So that's a particular correlation function. And on the bottom left, we've got those functions plotted in physical space. So you've got the separation distance along the x-axis and the correlations on the y-axis, and the different colors represent different length scales for the correlation functions. So the longest ones are the blue circles, L equals 10, then the red crosses at L equals 5, the black pluses at L equals 1, and the gray line is the identity, so just a diagonal matrix. And on the right-hand side, we've just plotted the same functions, but instead of plotting them in physical space, we're plotting them in spectral space by doing an eigenvalue decomposition. So the eigenvalues represent the uncertainty at a particular wave number. So the wave numbers tell you about the scale. The high wave numbers are for small scales, and the low wave numbers are for your large scales. So as we increase the length scale in the correlation function, we actually increase the uncertainty at large scales and decrease the uncertainty at small scales. So then when we think about using that information in a measure called the analysis sensitivity to observations, which is this formula S here, formula for S here, which is the background error into the background plus the observation error covariance inverse. And we've just assumed that we have an identity direct observation operator. And so the plot on the left-hand side are the colors represent the eigenvalues of this matrix S. And we fixed the correlation length for the background error as B, so that's LB, which was equal to 5. The wave numbers are along the horizontal axis, and the length scale of the observation error covariance matrix is on the y-axis. So when the background errors and the observation errors both have the same length scale, the analysis is equally sensitive at all scales. So that's the white bits in the picture. And when the observation error length scales are larger than the background error length scales, the observations are more accurate than the prior at small scales and less accurate than the prior at large scales. So that tells us that the analysis is actually more sensitive to observations of smaller scale features and less sensitive to larger scale features. So that acts like a high pass filter of the observation increments. When it's the other way around, so that the background error length scales are larger than the observation error length scales, the opposite is true. So you get a low pass filter of the observation increments. So we'll use this information later when we think about a real system with correlated observation errors. So before we can think about a real system with correlated observation errors, we need a method to estimate the observation error statistics. So we can do that using de Rosier et al. Measures, looking at the background innovations and analysis residual. And if we take a bunch of those and average over them, we'll get an approximate observation error covariance matrix. This is an inexact estimate. It depends on the statistics that you put into your analysis. And also, if you're using it with a system, an ensemble data assimilation system with localization, you need to be rather careful. But it's still a very useful method. So this is an example for Doppler radar that we did with the UK Met Office. And in this picture, this is just the Doppler radar wind configuration for the UK Met Office. So each radar beam produces observations of radial velocity out to a range of 100 kilometers. We've got observations every 75 meters along the beam, at every degree around the beam, and at 5 different elevation angles that you can see in the bottom picture. There's super-robbing to 3 degree by 3 kilometer boxes and thinning to 6 kilometers. And in the right-hand picture, we're going to look at the correlations around this blue circle, a particular, so we take a slice through the beam, a slice through the scan around the radar, and we look at horizontal correlations around that circle. So this is from the paper by Waller et al., Joanne Waller et al. from 2016, and because we knew that the de Rosier et al. Measure was sensitive to the statistics that we put in, we tried two different background error covariance matrices. We have an old one, which has a longer length scale, and a new one, which is in blue, and then the new one, which has shorter length scales, which is in orange. And we can see that increasing the length scale and variance in the assumed background error covariance that we're putting into the assimilation system reduces the variance and length scale in the diagnosed observation error covariance matrix. And that's consistent with some theory that we did on the diagnostic. So we can see it's sensitive, but regardless of how sensitive it is, we can see that the correlation lengths are a lot longer than the 6 kilometer thinning that we had in the system. So we know we need to deal with it somehow. Another example here, this is from the DWD system. So again, we did some work with one of our session chairs today, Elizabeth Bauern-Schubert. And we did a similar experiment to the experiment we did with the Met Office, but this time with the Cosmo Kenda system and the German C-band radars. And the top left plot is a plot of the standard deviation for the 0.5 degree beam. There's the standard deviation on the horizontal axis and the height on the vertical axis. And we've actually separated this by radar. So each different color line represents a different radar. And you can see kind of the purpley ones over to the right. Some of them fit rather nicely onto kind of a common line. But there's some of them that look a lot noisier and have a lot worse standard deviations. And they correspond to, in the bottom picture where I've tried to put the arrows, I apologize if it's a bit tiny. This is a picture of Germany with the locations of the radars, and the ones that have gone wrong are the ones I'm pointing to with the arrows, which are actually look out over the sea. And we discovered that those observations were contaminated by ship tracks and wind turbines. And so that's actually another use for these types of diagnostics, is that they, you produce them, they tell you something about your system, and if you do a bit of investigation, you can sometimes find the source of the error and correct it. So finding ship tracks and wind turbines is something you can correct by doing better quality control, and I know that was already underway at DWD when we did the work, and now that's been implemented operationally. So that's the DWD. So back to the Met Office. So we worked together with David. I think he'll be the next speaker now. David and his group at the Met Office to actually implement these spatially correlated errors in the Met Office system. I know he wants to talk about it, so I'm going to be quite careful about what I say so I don't steal his thunder. But I thought it'd be interesting just to talk about the scales of the increments, given what I said before. So on the right-hand side, there is a plot of increment length scales against model level height. So the verticals, the model level height, and the increment length scales on the right. And I've got 3 lines on the plot. The black line in the middle is our control. So that's the standard old operational setup, which is 6 kilometer thinning and a diagonal observation error covariance matrix, no correlations. And then we did 2 other experiments. So one where we kept the thinning the same. So we had the 6 kilometer thinning, but started to use observation error correlations. And that is the gray line. So in that gray line, we've got longer length scale increments. And that's consistent with the theory, because what the correlations end up doing is to be a low pass filter on the observations. They increase weight on the background. And actually, it kind of demonstrated to us that in the old operational system, the observations were being slightly overfitted. And then we did another experiment where we reduced the thinning. So we used the correlated observation error covariance matrix and 3 kilometer thinning. So we had 4 times as many observations in the assimilation, and that's the dashed line. And you can see there that you've got smaller length scales. So the increased observation density combined with the correlations means that you're more able to represent the smaller features. So that was very nice, and I'll let him to tell you all about the improvements that were found in forecast skill. However, it wasn't straightforward to implement this. It was quite a painful process because it required reparallelization of the Met Office data assimilation system so that the observations could be distributed in a different way across the processes. And David did it in a very clever way so that there wasn't an impact on the overall computation time. And this worked quite nicely for the radar data because we assumed that the errors were independent between different radars. It's not quite clear if the same method would actually work for other observation types. If the correlation error length scales are very long, and you've got observations spreading across the whole domain, so that each observation interacts with a lot of other observations. So that might happen if you think about making correlations for geostationary satellites. So I think that the method can be used for quite a lot of observation types, but not all of them so far. So that's an interesting open research question. So now I'm going to move on to the final section of the talk, which is about the future. And some of the things that are happening at the moment and might become future systems for hazardous weather forecasting, including some information about the models and some information about new observation types. So there's these hectometer models, so they're order 100 meter models, and these pictures are an example from the Met Office London model, which runs at about 300 meters, and it's run routinely, so it's not operational, but it does run twice a day, and that's run with a focus on urban systems. And you can see down the bottom the orography for the London model compared with the orography for the UKV, which is the 1.5 kilometer operational kilometer scale model. And research has already shown that this improves forecasts of fog, and that the London model, even down at 100 meter resolution, it partially resolves turbulence, but it has good bulk statistics. And that system doesn't have any data assimilation, and there aren't any current plans to put any data assimilation in, which doesn't mean that couldn't happen in the future. And the Met Office are not the only people with a model of this type. Indeed, there's going to be intercomparison experiment at the Paris Olympics in 2024 of these hectometer scale models. So that was a push downwards in grid length. The other way you could change things is to keep the grid length the same, but change the domain. So several places are thinking about doing global models that have kilometer scale grid lengths. So this picture on the left is an example from IBM, but ECMWF plans, there's the Riken Fugaku supercomputer, amazing supercomputer. And one of the things that makes me think when somebody like IBM starts getting involved is what are they interested in? There starts to become a bit more commercial ambition in terms of doing things. They talk about doing things like a personalized forecast for the street corner. And maybe there'll be more use of deep learning rather than just physical process-based models. The problem with these types of models is that when you're at kilometer scales, you still are in the convective gray zone, and you might still need to smooth your data assimilation in order to do good medium range forecasts. So maybe they're trying to solve a slightly different problem from the hazardous weather prediction problem by looking at a global model. So what is the right modeling approach for the future? Should we be thinking about keeping our models the same but increasing our ensemble sizes? Should we increase our grid length, increase our horizontal resolution to do hectometer scale modeling? Should we be trying to increase the domain size but keep the resolution the same and do global kilometer scale? Or should we be doing more coupled modeling and trying to couple with the land surface? And I think the answer to that question depends on really what you're trying to forecast, whether it's fog, floods, snow, ice, tornadoes, hurricanes, urban heat stress, air quality, or on what lead times you're trying to do it on. So whether you're looking at nowcasting timescales through to seasonal timescales, and also for who your users are and what they want, whether they're interested in probabilistic forecasts or deterministic forecasts, because what you can fit on your computer will vary. Okay, so very quickly now, because I think we're coming to the end of my time, future observing networks. So they're likely to be more heterogeneous. We're going to need to take a more pragmatic, flexible approach and use what we have to our best advantage and be ready to adapt quickly as new observation types come and go. We're also going to need to make better use of existing observations and be prepared to take advantage of new observation types, whether they're scientific observing missions, commercial observations, or non-conventional ones. So I have an example here of making better use of existing observations, where in our flooding from intense rainfall project, we made some corrections to reflectivity data for when the reflectivity data was attenuated during a large storm. So this in the plot here, you can see in the white areas, there's quite a big storm that caused a lot of flooding in London in 2007, but the radar picture, it looks like not much rainfall at all, basically because the storm was so big it attenuated the signal. And we used an idea from 19th century physics. It says all absorbers are emitters, and that enabled us to calculate the attenuation effect and correct the reflectivity. Part of the effect was from the radome, because some of the radomes, the little hat that sits on top of the radar, some of them were a little bit old and they were getting wet and having a layer of water on them. The newer radars didn't have that problem because they had a special coating that made the water go away. And then we were to correct the attenuation from the storm. Some of the dual polarization variables were used to do that correction. So I'm not going to talk in detail about that, but it's just an example of how you can improve observations. There's lots of new observing types coming online. We've got new satellites, these hyperspectral infrared sounders, drones, if only we can deal with the civil aviation issues. There's phased array weather radar, which produces fantastic observations, but is probably going to be quite hard to use, difficult to use those data and understand the uncertainty. Commercial weather observations, for example, CubeSats are very cheap to put up. But is there a danger with having more commercial weather satellites? There's already some data licensing problems appearing with commercialization of GNSS satellite data. And in the forecasting community, in the past, we've usually tried to ensure that somebody pays for the data only once and then it's made available to all the other weather forecasting centers for research forecasting, and of course the public good, which might not be the motivation of a commercial provider. So I just want to give a quick plug. There's going to be a WMO data conference in November, where some of these kinds of issues and open access to data and so on are going to be discussed. Further types of emerging observations include citizen networks, crowdsourced data, private weather stations are becoming part of operational systems, operational weather forecasting systems already, observations from vehicles and smartphones, and there's lots of research happening about those kinds of things all over the place. I'm not going to go into all the details of that, but if anyone is interested, I'd be delighted to talk to them about it, because I have a PhD student working with car data. Another WMO plug, there's going to be a verification challenge associated with using these non-traditional observations that has a closing date of next April. So if you're interested in finding new scores and visualizations and using those non-traditional observations, then do consider having a look at the WMO International Verification Challenge. All right, so my last slide. We began by reviewing all the issues in convection permitting data assimilation, and then we kind of looked in more detail at multi-scaling and how we can use observation error correlations to allow for the assimilation of denser observations and provide more detail at fine scales. We had a whirlwind tour of future systems. I kind of like to end on a question, because for a lot of the things that have come through time and time again through my talk is how can we actually measure observation impacts to ensure we get the most out of existing and future observations. So there we are, that's the end of my talk, and those are my references. Thank you very much.
Thanks to you, Sarah, for your nice talk and the questions and the view into the future. So let me check about questions. Is there a question in the speakers room of somebody?
I would have a question.
Okay, go ahead.
Sarah, you showed us a lot of different observations in the last part of your talk. So if you would recommend to a weather service or to a university, I mean, what would be your roadmap through these? Do you have a preference, or do you say, let's do it all at the same time, or how to source this? The scene is getting more and more foggy, really, with a lot of observations. Then, of course, we work on them, but I ask myself, what would you say?
That's a good question. I think it kind of comes back to my question I had at the end, is that it's actually really hard to evaluate because we don't have very good observation impact measures. I mean, I think the new things like MTG that have such large coverage are obviously going to be really important, but it also depends on the data availability that you've got. So things like car data could be quite difficult to get hold of because it requires commercial agreements and so on. So I think this is where the ability to compare between different centres, even though we've all got different domains and we might have a different perspective on our forecasts, we actually need to learn from each other, because we all, not everywhere is going to be able to work on all observation types all at once. But actually, if you can see the value that someone else has found by using a particular observation type, maybe then that helps you hone your strategy in the medium term. Does that make sense?
Yes, that's a generic answer.
Yes.
Yeah, I mean, I agree. Probably it's very difficult. It is tricky, and even impact. I'm always a little bit suspicious about impact, in the sense of, is it impact with the current system? Is it the impact we could achieve? How do we have to change our system to gain the impact we believe particular observations could give us? So it's a not clear, really.
Yeah. I agree it's not clear, but I also think you have to think for your system, what are the main weaknesses of your system, What do you know about your system, and which areas do you think you actually need more observations in order to improve, to avoid particular problems that you're having? So I think you I have to give a generic answer because I think it's going to be system dependent.
I agree. It's region dependent as well if you go to regional systems.
Absolutely, yeah. So if you're in the Great Plains of the US or the Alps, or East Anglia, or
Okay, so on Slido, I see there is one question, but I think it's a bit more general. So I would move it to the discussion later after the session.
Yes.
And so I think due to time, we will go on.
Okay.
Thanks again, Sarah.